Hello, am I audible? Hello, am I audible to you, Sanjay? Can you hear me?
Good evening, sir. I hear your voice, sir.
Okay, okay, okay. Thank you.
Sorry for the late reply, sir. Sorry for
Okay,
the late reply.
okay, okay. Don't worry. Are you able to see my screen also?
Yes, sir. It's visible, visible.
Okay, okay. Then okay.
Sir, whether any extra classes for exam related will be available, sir, or only the problem solving session will be available, sir?
Yes, I'm trying to conduct one extra session. Okay, but
Okay, sir. Okay, sir.
yeah, I
Okay,
request
sir.
you. Yeah, I request you kindly send me your doubt before the class, so that I will solve it and I will able to make you understand. So please, if
Okay,
you have
sir.
any
Okay.
doubt, you please write me. Okay.
Okay, sir. Sure, sir.
Huh. So it will be easy for
Sir,
me. Yes.
is
Yes.
there any previous questions available in net, sir?
Yes, the questions of last semester I have solved all the assignments questions, so you can go through it. This is
Okay, sir.
only yeah
Sir, not
available.
assignment questions, sir. That
Okay, okay, okay. Yeah, yeah,
exam questions.
yeah.
Exam questions, sir.
But it is not available with me. Yes, you can write to
Okay,
Professor Dhara, so he can help you
okay,
because I am only assigned to solve these assignment questions. Okay.
okay, sir. Okay, sir. If I mention in the questions, what to say that discussion area, whether they will forward me, sir, or I
Ha.
have to directly forward the message to him, sir.
Yes, you can write on forum and as well as on his personal email. So he will
Yes,
reply.
sir.
Might be, and you can CC me also. So if it is possible, I will also try to find out. Okay.
Yeah, sir.
Please,
Sure,
please
sir.
make me copy. Yeah. Just a minute.
Yes.
Hello, sir.
Yes.
Sir, actually, biaxially oriented polypropylene, when we biaxially oriented, it becomes like cr- cr- amorphous, like crystalline, no, sir.
So biaxial
We
arrangement.
orient, yeah, sir. When we
Has.
orient PP in
It should be
biaxial
crystallite.
direction,
Yes, it
it
should
is
be.
crystalline, sir. Sir,
Yeah.
the region is very small, sir. That crystallite region, is it only for BOPP and PET? In case any other polymers are also there, sir.
Yes, it is. The polycrystalline is depend on molecular weight also. If molecular weight is very low, then also it will not able to crystalline. So it should means it should have particular molecular weight also. Yeah, if it is in solution, how it will be crystalline like that?
Okay, sir.
Yeah. So it is also.
Thank you.
Uh,
Yes.
So it is depend on means it is vary from polymer to polymer. We cannot give a generic answer for all the polymers. Okay, it is depend as
Okay, sir.
yeah, as discussed in last week that you are able to see that only changing by one hydrogen by methyl group it is changing its crystallinity. So that are
Yes.
the actual situation. So we have to think all the
Okay, sir.
aspects of this polymer. Okay.
Actually,
Okay.
generally the crystalline, it will be opaque, right? No, sir.
If it is crystalline, then it is opaque. If it is amorphous, then it
Yes,
will be
sir.
a transparent.
It
Okay.
will be a
So
transparent.
what will happen in crystalline? They will form lamella. So light will
Yeah,
be
sir. It
scattered.
will
Light will
reflect a total light.
yes, light
It
will be
will
scattered,
scatter.
and due to scattering,
Yes, sir.
light will be reflect in a different angle. That is the
Different
reason.
direction. In
Hmm.
amorphous, there will be a space like
Ha.
excluded voltage get
Yes.
scattered inside and become transparent.
Yes, yes. So
Okay.
like EVA, you can see EVA. Some polymer are
Yes.
there that are means semi-crystalline, but also they are means transparent, like EVA, ethyl vinyl acetate. Are you able to, if you know, which is used as a encapsulant in photovoltaic module and many other electronic applications.
Okay.
Although it have a
Okay, sir.
crystalline nature and cross-linked also, but its
Transparent.
transparency is very high. So that's why it is used.
Okay, sir.
Yeah. So in the polymer case, we cannot make a general sentence for all the polymer. This is the case. But
Yeah, sir.
yeah, in metal we can say general type of sentence. But here
Okay, sir.
we have to think all these things. Okay.
Okay, sir.
Ah, okay, so now I am going to discuss about week 7 assignment question of last semester. Okay, so
Okay,
it
sir.
will help you to solve your current assignment.
Yeah, sir.
And after that, we will also discuss about the concepts which were taught in last week. Okay, so
Okay, sir.
yeah, let me start. Okay, so I think a few students have joined. Okay, yeah, it is already 606, so we should start now. Okay, yeah. I think my voice is clear and screen is visible. If any problem, you
Yeah,
can,
sir.
yeah, okay,
Yeah, that's for sure.
thank you. Okay, so it is week 7 assignment of last semester. Question number 1. Consider the following polymer processing process. Okay, identify the process that is associated with the lowest shear rate. Okay, so what is the importance of shear rate first of all? So actually, sir taught that when a shear rate increase, when shear rate increase, its viscosity is decrease. Am I right? So viscosity decrease means if viscosity is decrease, so the processing will be easy. Okay. If your solution is very viscous, highly viscous, then its processing will typically very hard compared to low viscous solution. Okay, so that's why we need a proper viscosity for different type of process. When you are processing your polymer by various type of process available, you need to select shear rate. Okay, so this shear rate will provide required viscosity, so you will able to process this polymer. Okay, so now just a minute. Student, I request you please join on time so it will not disturb again and again. Okay. Yes. Yes. So first of all, before solving this question, we should know about why we are worried about shear rate. Okay, because shear rate is generally you can say inversely proportional to its viscosity. Okay, so lowest shear rate. See, now again, what question is asking? Consider the following polymer processing. Identify the process that is associated with lowest. Okay, lowest shear rate means the process will be easy. Okay, and as you compare the calendering means you are making various layer like that. Okay, of polythene or like tetra pack, hexa pack. This type of packing are available in market. Okay, so this tetra pack it is made by a laminar sorry calendering. Okay, second is compressing modeling. Okay, so compression molding is simple. Okay, only you need to compress it and it will mold. Okay, suppose you have sheet, you just compress it and you will able to find out the required shape. Okay, then injection molding. So sorry, injection molding is also required very high shear rate because we need to decrease viscosity. Okay, we injection molding we discussed na. Extruder is there. Okay, from the extruder it is suppose this is the feed zone. Okay, from where you are, and one screw is there. Okay, I'm not able to draw a very symmetrical image, but just a minute, let me okay. Okay, one screw is lies there, it will rotate inside. Okay, actually its die will be higher. Okay, and here it will be feed zone, from where this is the hopper where you can put your polymer. Okay, and this is the screw, it will rotate. Feed zone, metering zone, and finally it is die. So it will be inject. Okay, so here you will put a mold. Okay, so the required shape of mold will be produced when polymer will be inject. Okay, so this process required very low viscosity melt. Okay, obviously it is very high, but as we are able to decrease the viscosity, okay, the processing will be easier. Okay, so here also we need little higher shear rate to decrease viscosity, and extrusion is same process. Up to here it is extrusion, it is just injecting na. So if it is more, if this mold is not here, okay, then it will make like that, it will make pipe or whatever. So this is called as a extruder. Okay, and extrusion process, this is extrusion process. So here also you need a very low viscosity. Okay, but in compression molding I think it require lowest what say lowest uh, uh, shear rate, because it can be done at high viscosity, because viscosity don't play a major role in here. Okay, so see, this is the answer B. Okay, B is right answer. Yes, compression molding is right answer, which has lowest shear rate. The value of shear rates are given here. Okay, if you are able to remember this value, then also you can answer. Okay, compression molding has lowest shear rate. Okay, we can also see in notes. Let me check if it is compression molding is there. 63. Yeah, are you able to see this compression molding?
Yeah,
Uh,
sir.
yeah. So see, compression molding, it do not play viscosity do not play any role here. Are you able to see? Only we need to put molding compound here, and it will press this, and it will we will get required shape like that. Okay. We just we will put the molding compound here, and just press this mold. Okay, and after meld, after press, we open and we will require shape. So viscosity don't do not play any role here in compression molding, but remaining all other process, remaining all other process, we required a low viscosity, which can make our process easy. Okay, so that's why this is the right answer. Okay, I think it is not always possible to memorize these values. Okay, so if you are able to understand the process, then you can correlate that which process required lowest uh, which lowest shear rate and highest viscosity like that. Clear this question?
Yes, sir.
Yes. Any doubt you can ask. Okay, don't worry. You can. Okay. So now we need to move question number two. Okay. So are you able to see this graph? This is stress strain graph. Okay. I think it is already explained many times. So you should know what is stress. Stress is represented by sigma. It is F upon A. Means force per area. Okay. F for force and A for area. Force per area sigma. And what is strain? So strain is means how much deformation is there. Okay, how much deformation is there, so we are measuring this deformation. Okay, so it is known as a strain. So so generally this graph can be understood by okay, so just a minute. Okay, suppose this is your sample. Okay, and you are pulling it from opposite direction F. Okay, means we are just measuring tensile strength of this sample. Okay, so what will happen when you pull it from the both direction, it should be deform. Okay, the size should be increase. Okay, it should be expand in this direction, and side should increase. Okay, so initially when you start force, sigma is nothing but force, only force per area. So you can, for time being, you can understand it is only force. Okay, so suppose you are applying force, so it will be deformed. So initially it will be deformed like that up to certain level. Okay, see, up to this point, this plot is linear, this graph is linear. It is representing that as I am increasing the stress, strain is also increasing. After that, also it is increasing. Okay, but it is a little bit deviate from the straight line. Okay, up to this point, this strain curve is proportional, you can say. After that, it is changing. So this behavior is little bit confucius. Okay, so we should know what is happening in our sample. Okay, so up to this limit, if you okay, suppose you are increasing sigma force. Okay, and after certain force, up to this point, if you remove this force, it will again come to its original position. Okay, but after that, suppose you have applied force up to here. Okay, stress up to here, then the sample will not able to reach again its original state. Okay, so up to here it is called as a means this deformation is reversible, but after that it is not reversible, so it is called as plastic deformation. Okay, plastic deformation means if deformation is there, then it is not you can say it is irreversible. Okay, so what is happening here actually, why it is not why it is irreversible? Okay, so actually up to this point, this sample is, you can say, intact, it is not damaged. Okay, but at this point it is damaged in the sense of one necking. Okay, so one necking will be formed at this point. Okay, so that's why this sample, if you remove the stress also, it will not able to reach its original state. Okay, that is the problem. After that you can see this necking, I think you are able to see this necking. Okay, what will happen if you further increase the stress, then this necking will be increased. Okay, and now your sample will look like, okay, this neck will be, the length of this neck will be increased. Okay, so this length will be increased. Okay, so after or you can say the polymer chains available in this necking area getting linear, like that. Okay, but at some certain point these all chains become linear, now they are not able to expand further. Okay, so up to this point this polymer chain became linears, and it is not now it is not able to further state by increasing stress. So what will happen, if you further increase the stress, at certain point this chains will be, this chain will be broken. Okay, so this is finally it is called as a broken point. Okay, so this is all over about the stress strain curve. So what question is asking, consider the stress strain curve and identify the point mark as 1 and 2. I think 2 is missed. Okay, 1 and 2. So 1 is yeah, this point up to from where plastic strain is increased, or the point up to where the elastic increase or say elastic deformation is there. This point is called as a yield stress, and the point where the polymer finally broken up is called as, it's called as break point. Yeah, okay. Yeah, sometime you will also ultimate stress. Okay, like that there are many terms. Okay, or break point. Okay, so A is right answer, and we can see further. Yes, so if you are able to see this diagram, it is clearly explained, okay, how the things are being happen. Okay, so again, stress and strain curve. Okay, see up to these are the linear elastic or non-linear elastic, but you can say up to here it is elastic. Okay, it is elastic deformation. After that, it is plastic deformation. Okay, so this point up to this point, it is representing elastic, that is non-elastic. It is linear elastic means uh, if you remove stress up to this point, the polymer sample again come to its original state by the same way. Okay, but if you further increase the stress, then you will able to see that uh, although here also the sample is able to reach its original state, but the way is different. Okay, so some loss of energy is there, so partial loss of energy is there. Okay, then necking will be created, so it will be plastic deformation, and then then necking will be expand and all things will be happen. Okay, then strain hardening. Okay, what is strain hardening means your polymer is lined up. Now again you are pushing, so now if finally it will be break point or ultimate stress or strain. Sometimes it is called stress, sometimes strain. Okay, ultimate stress or strain. Okay. So all other phenomena are explained here. Okay. So up to this point, where elastic deformation occur, it is called yield point or necking start. Okay, necking start, and it is called yield point. Yield stress and strain also. Sometimes it is also called yield stress, yield strain. So all these terms are similar. Okay, you should know about that. And it is elastic modulus from slope. Okay, so if you need to find out elastic modulus, then also you can find out by the slope of this curve. Okay, by if you are able to find out the slope of this curve, then you will able to find out the elastic modulus also. Okay, so up to here, where the where from where the sample again come to its original state by the same way, it is called as a proportionality limit. Then it is necking, the elongation by extension of neck. Okay, from, so you can see neck here to here, here to here, it is expanding. Then finally it is strain hardening. Okay, the chain are strained, and we are further increasing stress. Okay, finally it will be break point. Okay, or ultimate stress strain. Chain in neck align along elongation direction, standing. Okay, it is also called standing because chain are getting straight, and it is we are getting it is standing. It means it is making more tougher. Okay, because chain are now linear. Okay, and it is able to handle more stress like that. Okay. So I think this is clear. Stress strain curve. Any doubt up to here? You can ask. Okay. So now we are going to discuss question number 3. Time dependencies of elongation are measured by. Okay. See, time dependency of elongation. Okay. So we are not applying any force here. Okay. Time dependency means with time something is getting elongated. Okay, with time something is getting elongated. Okay, simply you can say by gravitational force only. Okay, due to gravitational force only, something if is elongating, then you can say it is a time dependent elongation. Okay, suppose this is one strip. Okay, and it is hanged like that. Okay, this strip is this is a metal strip, you can say made of lead. Okay, made of lead PB. Okay, and it is hanging like that. T is equal to 0. You observe that T is equal to 0. Okay, this is length. But after suppose T is equal to you can say 24 hours. After 24 hours, if you are able to see the same sample. Okay, if you are able to see after 24 hours, the length is increased. This delta L is increased after 24 hours. Okay, so why it is happening? You are not applying any force. Okay, it is only due to gravitational force, or due to, you can say, loosely bond of atoms. This is elongating. Okay, so this type of elongation is also present in polymer. Okay, and this property is known as. Okay, so this question is asking what is the how we measure this property. Okay, so this property is known as a creep. Okay, so elongation with time without any force. Okay, only gravitational force is there obviously, but otherwise not, you are not applying any external force. So it is known as a creep test. Okay, so this is the creep test, and this phenomena is known as creep. It is very common in metallurgy, and also it is found in polymer. That's why it is being taught here. Okay, see. So this spring is, you can see this spring. Okay, and it is also showing the creep behavior. Okay, this is at time is equal to 0. Okay, And after, suppose you can say at time is equal to uh, any 6 hour. Okay, so after 6 hour, this is elongated. Okay, without any force. Okay, so this elongation delta L is known as creep property. Okay, this is very important term. Okay, please remember this creep. Okay, then question number 4. Select the energy change. Sorry, select the energy changes associated with the following process. Okay, we have already discussed this in detail in last question. Elastic deformation and inelastic deformation. Okay, so obviously in elastic deformation, we will able to again means elastic deformation means if you remove the stress, the specimen or the sample will again come to its original state. Okay, it will not lose of any energy. Okay, no loss of energy. But in inelastic deformation, there is some loss of energy in inelastic deformation. Okay, yeah. So obviously D will be right answer because sorry, elastic deformation no loss of energy, but in inelastic deformation it is a partial loss of energy. Okay, we have just discussed it is graph like that, na? Then okay, it is little deviate from the straight line. Okay, so then it is yield point and all. Okay, so it is little deviate and it is called inelastic deformation. See, I already told you that means crystalline. If it is crystalline, it should be opaque, but it's also depend on how much it is crystalline. Okay, so its transparency depend on its percentage of degree of crystallinity. Crystallinity. Okay, we discussed now how much polymer is crystalline. Okay, so 100% transparent is not possible. But if you increase the crystalline nature in polymer, it will become opaque. Okay, and it is also depend polymer to polymer. Okay, you asked question at 601. Okay, sorry, it is the only, yeah. So question number 4, I think it is clear. Okay, so this is the detailed solution of question 4. Elastic deformation is said to have happened when the material returned to its original state on releasing the stress, following the same stress strain curve. Okay, as it is increasing, again it will be decreasing. So same path will be followed. Okay, that is during the deformation. No loss of energy. Yes. Okay, so elastic deformation is clear. Now in inelastic deformation, where it is a little deviate from the straight line. Okay, if at all sample return to original state along different route. Okay, it is not from same route, along with different route, but if at all sample return to its original state. Okay, it is coming to its original state, but by different route. Okay, so in this process there will be loss of energy. Okay, so partial loss of energy. Okay, that's why this answer is correct. Okay. Okay. So now question number 5. For a semi-crystalline polymer, the thermodynamic transition associated with Tg and TMR. Okay. So, if you gone through lectures which were taught in last semester, TG is second order and TM is first order transition. Okay. So C will be right answer. Okay. It can be explained a little bit in detail. Just let me give some time. Okay. It is around. Okay. So see, thermodynamic. I think you are able to see this. Slides, thermodynamic of TM and TG. Am I right? Are you able to see?
Yes, sir.
Yes.
Yes, sir. It's visible.
Okay, okay. So see, thermodynamic or TM, TG. Okay, so we will able to find out how it will be vary. So thermodynamic transition, first order or second order. Okay, so there are two type of transition, first order and second order. In a first order, G is a function of any state variable which are VPT, where volume, pressure and temperature is continuous. Continuous, are you able to, continuous means this graph is continuous like that, okay? Either like that, either whatever graph, but it is continuous, okay? Okay, so in first order, G as a function of any VPT is continuous, but in first partial derivatives of G, okay, but the first partial derivative of G with respect of state variable are discontinuous. Okay, so first uh, first partial differentiate. Okay, so first partial differentiate will be discontinued. Okay, means you will able to graph, you will see able to graph like that. Okay, it is discontinued. Okay, same for glass transition in first order it is continuous, but okay, in first order you will able to find this type of graph, but in second order of differential partial derivation, you will able to find out this discontinued graph. Okay, that's why this is the first order and second order. So TG is second order and TM is first order. Okay, so we can further understand. Just a minute, somebody in waiting room, I think. Okay, so suppose this is the G. Okay, this is the graph G versus uh, T, temperature, volume, pressure. Okay, whatever. So it is means continuous graph. Okay, but in first order deviation, okay, which are V minus S in entropy. Okay, V volume, entropy, and H. If these are plotted with this state terms, it will you will able to find discontinued graph in first order. Okay, so for uh, TM you will for melting point you will able to find this type of graph. Okay, I think you know about this graph TM. Okay, suppose temperature versus no. Okay, volume versus temperature if you plot the graph. Okay, for Uh, Suppose you are for semi-crystalline only. For semi-crystalline, you are able to for semi-crystalline. If you are plotting this graph, okay. So what will happen? You will able to find this type of graph. Okay. So suppose if it is for crystalline, if it is purely crystalline, then it will be like that. Okay. So here you can say somewhere Tg. Here somewhere you can say Tm. Okay. But for pure crystalline, it is Tm. Okay. At Tm only, at Tm the volume will be increased drastically. But in semi-crystalline, it will be look like that. Okay. So this is the continuous graph. For Tm, it is continuous here for volume measurement. Okay, now it is first derivative graph. So if Tm is first order, so its first derivative graph also should be continue. Okay, then only you can say that it is a uh, just a minute. Okay, so these are the other information we will not discuss. V minus h and s. These are the first derivative. Which okay. So for here, g with v minus h and h will be continue. Okay, for first order. For but tm and this will not continue. Okay. Okay. So tm, I just discussed about the tm with volume. Okay, and we found that it is not continued. Okay, but in first order g. Okay, so we need to plot g first order derivative of g with the volume. Okay, then we need to find out that how much Gibbs energy is changing. Okay, so also you will able to see. Just let me show you. Okay, suppose this is the. Or you can say simply g. Okay, g with temperature. So at melting temperature, it the this will be discontinued. Okay, at some point you can say T is equal to Tm, the Gibbs energy will be increased drastically and it will make discontinued graph. Okay, first derivative graph. Okay, detailed solution in the first order g as a function of any vpt is continuous, but the first partial derivative of g with respect to state variable are discontinued. Okay, so these are melting and vaporization. Okay, and in second order, the first partial derivative are continuous, but the second partial derivative of g are discontinued, like glass transition temperature Tg. Okay. Then question number 6. So what question number 6 is asking? The value of glass transition of the following three polymer is given. Okay. These are the Tg's. Okay. For polyethyl methacrylate, poly N propyl methacrylate, and poly n butyl methacrylate. So methacrylate is same, only poly these groups are changing. Okay, ethyl, n propyl, n butyl. Okay, so what should be happen? See, ethyl, n propyl, so it is increasing. Okay, n propyl, ethyl to n propyl, n propyl to butyl. So so carbon number of carbon is increasing as we are moving down. And what question is asking, what is the nearest value of Tg? We need to find only idea. Okay, nearest value of Tg of polyisopropyl. Okay, so isopropyl means it is n propyl. So n propyl means it is C C C like that. Okay, it is n propyl, and in isopropyl it is like that. Okay, something is there, like otherwise it is like that. Okay, so what we need to find out that what is the nearest value of Tg. Okay, so it is n propyl, it is has 38, but as we increase one more carbon like that. Okay, so it will create some steric hindrance. Okay, so Tg should be higher, means it should be higher than 38. Okay, it should be higher than 38, but it is yeah, it's so 38 higher than 38 only 50. So I think 50 is right answer. Okay, because yes, 50 is right answer. So let me explain again. Isopropyl substitution increase the steric hindrance. Yes, it is given here. Okay, isopropyl substitution increase steric hindrance for the rotation around the single bond in comparison to n-propyl substitution. Okay, so n-propyl, if n-propyl substitution is replaced by isopropyl substitution, it will create steric hindrance and Tg will be increased. Okay, but in plasticating, okay, so what plasticating means, it will allow polymer chain to move easily. Okay, so if you are adding some plasticizer, it is also making same thing. Okay, making polymer chain means more easy to move, easy to flow, or easy to adjust, whatever. Okay, so but in plasticizing, if carbon chain is increasing, the plasticating will be increased. Okay, means polymer chain will be able to move easily. Okay, so obviously in if you compare ethylene to propylene, okay, so also it is creating stirring hindrance, but it will also provide some plasticity. Okay, so that's why its Tg should be higher than n propyl, but should be lower than yes, but should be but it is plasticity more than ethylene group substituent. Hence, the Tg value of isopropyl methacrylate should be higher. Okay, then n-propyl methacrylate, but less than polyethyl methacrylate. Okay, so from polymethyl methacrylate, it should be less. Okay, because why it is less? Because it is providing some plasticating property. Who providing this isopropyl compared to ethylene isopropyl providing more plasticating property. So its Tg should be less compared to ethylene methacrylate, but it will be higher compared to n-propyl because it is creating some stirring hindrance. Okay, so I think it is clear. Hence, among the option given, the Tg value of polyisopropyl methacrylate should be 50. Okay, only this value is appropriate. See, these are because higher than 38, only 50 is given. So no need to confuse. If you are not able to correlate with ethyl methacrylate, then also it is not problem. Okay, because no other value is given. If there is 60 is given in one option, then you need to make some common sense and like that. Otherwise, it is okay. Okay, by having some knowledge, you can answer this question. Clear? This question is clear? Okay. So now we are moving to numerical question. Okay, question number 7. Estimate the glass transition temperature in centigrade of random copolymer. Okay, it is random copolymer. See, of vinyl chloride and vinyl acetate containing 14 weight percent of vinyl acetate. The Tg of polyvinyl chloride and polyvinyl acetate homopolymer are 88 sorry and 32 respectively. Okay, so Tg is given. We can say Tg1 and 2. It is given. Then weight percentage is given. One because it is copolymer and it is random polymer. So one weight percent is 40. Okay, weight percent one is 40. Then weight percent second will be obviously 60. Okay, so this value is given. This value is given respectively. Use Fox equation. Okay, it is hint is given here. Use Fox equation for calculating Tg. Otherwise we need to worry that either this vinyl chloride and vinyl acetate are miscible or it have some type of interaction and all things. Okay, so we need to use various formulas are given here. Okay, and it will be a little complicated, but it is already given here. Use Fox equation to calculating copolymer Tg. Okay. So I think you know about the Fox equation, how to find out Tg, Tg of copolymer of a, okay. So it will be weight percent upon Tg first plus weight percent of second. Okay. So this formula if you will use, you will able to find out Tg of this copolymer. Okay. Simply you need to put the value. Okay. So you will able to find out the answer. Okay, so it is solved here. So weight fraction, okay, so not weight percentage, weight fraction we need to put here. Okay, so see it is zero point 0.4 plus 0.6, 305 plus 361. You can solve it. I think it is very common maths. Nothing is here. Okay, so
Sir, what is the temperature again, sir? Can you show me the question, sir?
temperature, Tg temperature.
Yes, sir. For A and B, sir, here 8832 in degrees Celsius, sir, but they have mentioned
Yes,
305, sir. They have
ha,
converted into Kelvin, sir.
Kelvin. Yes, yes. They have converted in Kelvin. To
But we
seven.
are need only in degree only, sir.
Ha, but we especially we
Why need
yeah.
if it is everything is in degree? We just
Yes, you are right. But I think there is actually in lecture also, sir mention especially that you need to put this temperature in Kelvin only. Then only you will able to find correct answer.
okay, sir.
I think something is
Then
there.
after finding, I have to
Ha, convert again.
again convert it into
Yes. Yeah. Actually,
okay, sir.
I didn't
Fine, sir.
I
Fine, sir.
also didn't find the root cause of this problem, but somewhere sir explained that we need to put in Kelvin only. That's why these are the this is like that. Okay. Okay, so this is clear. Question number 7 is clear. Any doubt? No?
Sir, your voice is not hearing, sir.
Yeah.
Sir, come again, sir.
So question 7 is clear, na?
Yes, sir.
Question.
Yes, sir. Okay, sir. Okay,
Ha,
sir.
ha, okay, yes. Just. Now we are moving question number 8. Okay. Consider the following two polymer with similar molecular weight. Okay. Polymer A and polymer B. Find out. the following statement is correct. A crystalline, B crystalline. Okay, so we need to find out the crystalline nature with respect to their structure. Okay, so molecular formula is given and its structure is also given. So we need to find out that whether it will be crystalline or not non-crystalline. Okay, so see, according to symmetry also we can find out na, that it will be crystalline or not. So in case A, it is crystalline. Okay, sorry, it is symmetrical. Okay, one CSC group is there here and another is here, so it is symmetrical. Okay, but in case B, it is not symmetrical. Okay, if one side it will be hydrogen only, na. One side is CSC, another side it will be hydrogen, so it is not symmetrical. Okay, so on basis of this, we can say that polymer A will be crystalline. Okay, because it is given here only crystalline or non-crystalline. Okay, not semi-crystalline is not playing any role here. Okay, so either it will be crystalline or non-crystalline. So we can say then that A will be crystalline and B will be non-crystalline. Okay, A will be crystalline, so D is the right answer. A is crystalline and B is non-crystalline. Okay, so according to symmetry, you can predict that whether it will be crystalline or non-crystalline. Okay, clear? Understood?
Yes, sir.
Okay. Okay. Yes, it is higher the symmetry of the polymer, higher is the crystalline. So polymer A is more symmetric where okay, take it. Yes, yes, you can answer. Screen not visible.
Sir,
Uh,
visible, sir. Visible, sir. You proceed, sir. Understood, sir.
yeah, means but Bakia, she is not able to see my screen.
Okay, sir. Okay, sir.
Huh. So are you able to Bakia? What is your problem? Are you are not able to see the screen because other students are able to see. So I think it is not problem from my side. Can you just check your connection once more?
Yours is clear only, sir.
But yeah, some okay. It might be some problem from her side. Okay,
Okay.
so yeah, it is clear now. Question number 9. Okay, so question number 9 again. It is asking that on decreasing each of the following, which one will generally increase the TG? Okay, we the various parameters are given here. If you are decreasing this parameter, then which one will generally increase the TG? Okay, so means which is inversely proportional, we can say. Okay, so number of polar group present in polymer backbone, then Tg will be increased. Okay, if number of polar group present in the backbone, then it will make some type of bonding like hydrogen bonding, polar bonding, and whatever more stronger bonding. So Tg will be higher. Okay, so if polar groups are present in backbone, then Tg will also increase. Okay, so this is not right case. Okay, so A is not right case. Then stiffness of the polymer backbone. Obviously, if stiffness increasing, then Tg also increase. Okay, we discussed about that. So it is also wrong. Then concentration of added plasticizer. See, this is the right answer because if you add, if you add, if you decrease the concentration of plasticizer, Tg will be increased. Okay, because what is the work of plasticizer? It will allow to make polymer chain more flexible. Okay, it will be able to move and like that. So that's why if you reduce the concentration, then chain will be not able to move easily. Okay, so that TG will be increased. Okay, so this is the right answer which we are finding. Okay, then also last, molecular weight of polymer, as molecular weight of polymer will be increased, Tg also increase. Okay, so this is all the case which is inversely proportional. Okay, So C is right answer. Okay, clear? Okay, last question. So it is already given. Presence of plasticizer increase free volume. Okay, obviously, so that chain will be easily move. Hence decreasing it increase TG of the polymer. All other three factor decrease the TG of polymer upon increasing the parameter. Okay, we have discussed in detail. So question number 10. Now, which of the following thermodynamic parameter change discontinuously on hitting a polymer beyond Tg? Okay. Which of the following thermodynamic parameter change discontinuously on hitting beyond Tg? Okay. So beyond Tg, which will be coefficient of thermal expansion, I think, because it is second order reaction. So D should be right answer. Yes, yeah, it is given here. So glass transition is second order transition, which means that second derivative of Tg will respect to VTP change discontinuously, whereas the first derivative change continuously. Okay, so V and H are given by the first derivative S on below, whereas heat capacity and coefficient are given by second derivative. Okay, so here which the following term change continuously on heating a polymer beyond Tg. Okay, so D is right answer because it is a second order derivatives. Okay, so these are the questions. I need to discuss, which make your assignment easy. Okay. If you have any question, you can ask first. Any question up to here? Okay. So any question you can ask up to here, if you want to ask. Otherwise, we will take 5 minute break. Okay. Then we will start again, and I will just discuss concepts which were taught by sir. Okay. If you have any doubt, you can stay here. Okay. It will help you to uh, means uh, it will brush up your concepts only. Okay, so you can stay here, but after 5 minutes we will start. Okay, so please be there at 7:06. Okay. Okay, student, I think you are here. Okay, so you do not, if you do not have any doubt, I will discuss about concepts which were taught in last week. Okay, we move fast. Okay, so that we cover more. So in the last week, we discussed about polymer and polymer processing. Just let me in. Somebody in waiting room. Yes, Sandhya. Yes, Sandhya. What happened? Tell me, Sandhya. Yes, you can ask, Sandhya. If you are in doubt, you can ask. What happened? I think she left. Okay. So in last week we discussed about the polymer and its processing. Okay, because polymer processing is very important to make desirable product. Okay, because if you when you synthesize polymer, they are in powder, pellet, or emulsion form, which do not have any use. It can be used for a chemical reaction or otherwise it do not have any use. So to make this polymer useful and to make a desirable product, we need further processing. Okay, we need some additives. Okay, which improve the quality of polymer so that it can use for domestic, industrial, and other applications. Okay, so you can say polymer is a starting product from where we can make our desirable product. Okay, so it's processing, design, fabrication, finishing, then final assembly. Okay, these all steps are included to make polymer to valuable product. Okay, so we will discuss more about that processing. Okay, how we can process. So polymer can be formed, cast, machined, and joined with relatively easy. How it is easy? Because metal is hard enough, we know, and metal is heavy. Weight is heavy, hard, and it is not efficient compared to polymer in some aspects. Okay, that's why polymer can be formed, cast, machined, and joined with relative easy compared to metal. Require little post processing or surface finish operation. Okay, because metal product or wooden product, they require a very high surface finishing and all that, but polymer is also already very good finished, and also it has surface which is hydrophobic sometime, and also inert to many chemicals and conditions which are generally found in our domestic and industrial purpose. So it is so polymer are resist to this type of conditions. That's why it can be after post processing it is easy. Polymer melt or cure at relatively low temperature. Yes, okay. Because if you talk about the metals, they require generally thousands of 1000 degrees centigrade of temperature, but this polymer can be melt in hundreds. Okay, so polymer require less energy to process than metals. Okay, because it melt in less temperature compared to metal, so it require less energy. Okay, polymer are used to make a reinforced polymer part. Okay, like we can make composite by using polymer. Okay, it will make some composite type of structure which is absent in metals. Raw materials cost commonly are pellets and powder. Okay, so generally the industry which produce various products of polymers, they just purchase pellets and powder of polymer, then they further process this polymer to make valuable product. Okay, polymer family, thermostat, thermoplastic. Okay, so according to their property, these thermoplastic and thermoset have different type of processing. Okay, so we need to think what are the. Okay, so some examples are given here. Okay, thermosets which can, thermoplastic which can be reformed again. Okay, when melted it can be reformed, but thermoset do not. Okay. This is the structure of thermoplastic, amorphous and semi-crystalline. Okay, in amorphous region, it is looking like looking like means entangled chains. Okay, but in semi-crystalline, where is some lamella of crystalline part and some amorphous region can be seen in semi-crystalline. Whereas in thermoset, where in thermosets, cross linkings are there. Okay, these are the cross linking bonds which are formed, and due to formation of this cross link, this cannot be reformed again. Okay, so once these bonds are formed, it cannot be it cannot be break, and cannot be reframe again. Okay, so it can be used single time. Okay, only it can be it can be stress. Okay, so it can be used as elastomer. Okay, yes. Then processing of thermoplastic. Okay, so thermoplastics are very common and very widely used polymer. Okay, so it can be either melt if it is pure what say if it is pure polymer pellets or powder, we can melt it, or suppose it is in solution, so it can be cast directly. Okay, if it is melt, then it can be extrusion, directly extrusion or molding. Okay, by extrusion it will make product like pipe and what say uh, poles, pipe, sticks like that you can make from extrusion, where from molding you can make 3D type of shape. Okay, various important shape for automobile, for industrial use and various other applications. Okay, so sometime melt also spine and make fibers. Okay, so from melt we can directly make fiber by spinning. Okay, so these are the various type of way which we can deal to process our thermoplast. Okay, so uh, with the perspective of industrial use, the extrusion is the most important technique of processing. Okay, so by extrusion, many polymers products are being made. Okay, you can see it is 36%. Then again, injection molding. Okay, so injection is 32. So injection molding is also part of extrusion. Okay, extrusion is only making some uh, it is extrusion, so it is making only means a continuous product. Okay, like pipe and whatever. But in injection molding, from the extrusion, we are putting some mold, some required mold which can make desired product. Okay, so these two techniques are very important. Injection molding is, you can say, modification of extrusion molding. You are just putting one extra mold at the discharge of extrusion, which okay. So this is the again one schematic which represent the processing. Okay, initially we add resins, additives. Okay, various type of additives which we used for coloring, for reinforcement. Okay, to increase hardness. Okay, so various type of things are available. We sometimes sometimes we use regrind means we are just recycling the polymer which is coming which is producing as a waste in the processing or some extra part by cutting and whatever. So we are putting this scrap as a regrind. Okay. Sometime we also use master batch, which is nothing but concentrate solution of additives and like that. So we are adding this all thing. Then extrusion, so it will make product directly like pipe and this type of things. Or we can, yeah, pipe and profile, okay, it can make final product. Or we can add filler, reinforcement. Okay, so if we add these fillers and reinforcement, okay, to increase its property, then it can be used for injection molding, blow molding, thermoforming, and compression molding. Okay, so after extrusion also we can make it. If we are adding foaming agent, sorry, then it will make fiber spinning, cast film, blow film, etc. Okay, so amorphous, if your polymer is amorphous, okay, so it is operated TG plus 80 to 140 degree centigrade. Okay, more than means it is more than TG. It should be higher than 80 to 140 degree centigrade higher to TG. But if it is semi-crystalline, then it should be, then the processing temperature should be higher than its melting temperature, more than 20 to 50 degree centigrade. Okay, so this is the extrusion machine and it is extrusion process. So this is the feed from where you mix polymer additives and all. Okay, then it is grind, and due to friction, some temperature will be increased here. Sometime here the heater is also provided, okay, to increase the temperature. If it is not provided by friction only, then we need to use some heating element. Okay, finally it will be melt here, and finally then it will be come from this die and produce a desirable product. Okay, so it is most common in polymer industry, this process. So most commonly manufacturing of plastic resin, combined pigment additives and resin, heat, high heat, high pressure. Okay, so this pressure is created by this screw which is moving in the barrel. Okay, this is called as barrel. This complete assembly is called as barrel, and under this barrel one screw is there. It is continuously rotating, and these are the wings which are helping to flow mm, this polymer and additives and all to move on. Okay, move in forward direction. So pushed through die. Okay, finally it pushed through die. Okay, this is the outlet, so it is pushed through die and shaping through die also. Okay, so the final structure will be depend on the final opening of die, then creating warm plastic of possible further finishing operating such as pelletization, calendering, or molding. This is the steady state process, high productivity, then low complexity of part, sorry, low tooling cost, and wide tolerance. Okay, so according to your application or according to the required property of product, we can make we can change the size of this screw. We can increase temperature. Okay, we can change also the speed of this screw. We can change also dimensions of this various part of this screw and all. There are many parameters which can be played to make required product. Okay, or if your polymer has because each polymer do not have same property. Okay, so we need to think that what is their viscosity and what are the how much percentage of polymer additives you are mixing, and we need to play all these things to make the required product. Okay, so this is about the extrusion process. Okay, now see injection molding. I told you before that extrusion process and injection molding are just similar. Only what is difference in injection molding is that we are providing a extra mold in injection molding. Okay, so see up to here it is almost same, okay, but here you provide one mold, okay. So by now this cylinder is pushing this melt polymer material into this mold, okay, and it is compressing injection molding, okay. So it is making some compression, and finally the melt polymer will be sprayed in this mold, and acquire required shape, okay. So this is the injection molding, and it is making very good quality product, okay, which are being used for industrial use and in automobile and domestic purpose also. So this is widely used technique. Extrusion is widely used technique in, and in second number, injection molding is used. So pellet granules or powder are fed into the heated cylinder, then forced into the die chamber by hydraulic. Okay, these are the simple thing. I think you know about that. So product of complex shape of various size, high production rates, costly tooling, whatever. See. Now, this is also one type of extrusion only, extrusion blow molding. Okay, so up to extrusion is same. Up to here, see it is same. Up to here, it is extrusion only. But from the extrusion, we are making parison as a middle product. Okay, as a middle product, we are making parison. Then we are fixing this parison in particular mold. Then we just blow by the air. Okay, so by blowing this air, this parison will be elongated, spread, and acquired required shape. Okay, so parison descent, then inflating. After after that it require shape, then cooling, and finally injecting. Okay, so this is the steps which is used in blow molding. Okay, so the product of blow molding, you can say these bottles. Okay, very simple. Okay, you can understand. So this bottle initially parison was made. Okay, small bottle, you can say, means the demo of the bottle. Okay, it is known as a parison. Then this parison is further treated, and it is blown in the mold so that it can make required product. Okay, so it is called as a extrusion blow molding. In extrusion blow molding, a parison, a tubular profile. Okay, it is a tubular profile. Here you can see. Okay, so in extrusion blow molding, a parison, a tubular profile is extruded and inflated into a cavity with a specified geometry, then clamped and air blown inside to expand it to fit a much larger dimension mold. The blown article is held inside the cavity until it is sufficiently cooled. Okay, because if you are opening this mold in in heated condition, then your product will be damaged. Okay, due to fast cooling and whatever, because it is very viscous also, highly okay, because it is not, you can say it is rubbery solution only. It is not acquired its glassy state. Okay, so we need to remove it after it's acquire lower temperature compared to its TG. Then only we can open. Okay, so there are some type of injection blow molding, multi-layer blow molding, rotational molding. Okay, so multi-layer blow molding means we are making various type of layer. Okay, tetra pack, hexa pack, like that, tetra layer, hexa layer, like this type of molding. Okay, otherwise the concept is same. The rotational molding is little different. Okay, so we can understand rotational molding. Suppose these are the two mold. Okay, at each end of, okay, so suppose these are the two mold, okay, and let me write name of this mold. This is the one, and this is the second mold, okay, and it is rotating in this direction, okay. So it will be rotating, but it is rotating on its own axis also, like that, okay. So this is called as a rotational molding, okay. So it is rotating on this axis. Okay, it is rotating on this axis and it is also rotating on this axis. Okay, so it is a pre-measured quantity of powder. So what we do, first of all, these are the mold, one and second. So pre-measured quantity we just filled in this mold. Okay, pre-measured quantity, first of all we need to fill. Okay, then rotate on two axes. Okay, so are you able to, I think you are able to understand how it is rotating on two axes. So rotated on two axes inside the heated furnace. Okay, so it is some arrangement is there which will heat this mold or this furnace. Low equipment cost, low pressure time, low process, longer process time. Okay, obviously it will require longer process time to uniformly distribution of materials. Okay, and trash can bottle hulls, yeah, it can be made by boat hulls and trash cans. This can be made by this process, low quality product processes. Okay, okay, so we need to discuss these two more process. Structural form molding. Okay, so what structural form molding is doing, we are just providing nitrogen. Okay, so it will make some free space. Okay, it will make some structure. Okay, which has some space, some voids, which and which will be created by nitrogen. Okay, so a variety of injection molding process, particularly for large structure part consists of rigid closed cellular core surrounded by continuous solid skin. Okay, closed cellular core. Okay, so some cells are there, means some voids are there, and it is surrounded by continuous solid skin. A much lower pressure operation than the conventional injection molding type, which allow much larger part to be molded. Okay, so in injection molding we required very high pressure, but here it is not much higher is required. Then thermoforming, it is very simple. This is the polymer sheet. You increase the temperature and acquire vacuum, so it will be pulled up and acquire the final shape of this mold. Okay, so whatever shape you require, according to that you can put the mold. Okay, so a plastic sheet is heated to shake point, soften but not melted. Okay, see, only it should be softened, not should be melted. Heated sheet placed over a room temperature, mold and force against by vacuum pressure. Okay, then we require vacuum pressure. So these type of products are used for appliance of housing, packaging, advertising signs. Okay, so refrigerator liner, etc. Okay, so low quality product will be formed. Then finally, this is the thermoset polymer. Okay, up to here we discussed about the processing of thermoplast polymer. Now, this technique is used for thermoset polymer, which is compression molding. It is very simple type of process where we just put the molding compound here and just press it. So it will make some type of chemical bond, and finally it will make product. And after that it will not again reframe. Okay, we cannot reuse it. Okay, so once the bond are formed, it is permanent. So coloring of rubber means where if you are making various rubber of various layer. Okay, so it is used in coloring. So coloring is the process of producing long run for uniform thickness sheets of rubber, either unsupported or fabric baking. Okay, it can be whatever. A standard 3 to 4 roll calendar with liner speed range 2 to 10 feet per minute is typically for silicon rubber. It is not for our case. Okay, reaction. So chemical reaction between two polymer materials will be there here by the pressure. And this question is also this slide is also discussed in one question which I solved in assignment. Okay, so what will happen? Viscosity will be decreased. Viscosity will be decreased as strain rate will be increased. Okay, so sometime in some process we require higher strain rate. Why we require higher strain rate? Because at higher strain rate the viscosity will be decreased. Okay, so viscosity will be decreased, so the processing will become easier. That's why we require very high strain rate in extrusion injection molding. You can see very higher strain rate we require. Okay, why we require higher strain rate? To decrease the viscosity of polymer. Okay, but in compression molding where we do not require any flow of material and all, so it's okay if strain rate is very lower. Okay, so now we are going to discuss about the mechanical property of polymer. Okay, we all know that traditionally where metals were being used since long time, now metals are being replaced by polymer material, by fibers. Okay, why? Because its chemical composition, okay, due to its resistance to corrosion, okay, due to its lightweight, low cost. Okay, so there are many reasons which make polymer uses beneficial. Okay, polymer provide good mechanical property at a reasonable cost. Okay, so cost is the main factor to make any product viable. Okay, so if cost is reasonable, then obviously if two products are there and cost, if uh, a huge difference in cost, then obviously person will try to use lower cost material. Okay, if their properties are comparable but cost is very lower, which is case in our metal and plastic. Okay, somewhere metal are playing very good property, but the cost of metal is very high. So then it is replaced by polymer, and there are many property which are showing only by polymer. It is like lightweight and non-conductor of heat, and these are the unique property of polymer. Okay, so uh, at that time, at that application we need to use only polymer. So the property of polymer also depend on the chemical composition, molecular weight, branching, cross linking, crystallinity, orientation. Okay, whatever we have discussed. Okay, so mechanical property. So viscoelasticity, what is meaning of viscosity is generally used for liquid. Okay, and elasticity used for polymer, like that. So viscoelasticity means we are trying to explain this both phenomena in one term. So viscoelasticity implies that the material has the characterization both the viscous liquid and elastic solid. Okay, so what are the viscous behavior? Cannot support a stress without flowing, causing permanent deformation. Okay, so these are case in polymer. If you are applying the stress, so it will make some permanent deformation also. Okay, so it is a property of viscous polymer, viscous liquid. Then elastic behavior, complete recovery of imposed deformation or removal of imposed stress. When you remove the stress, it will come to its original structure. This is called elastic behavior. Okay, so polymer showing this both type of behavior. That's why it is known as viscoelasticity. So elastic deformation, inelastic deformation, and plastic deformation we have already discussed. So I think there are some tests to find out mechanical properties of polymer. Static tests like tensile, compressive, shear stress, impact test. Okay, so which uh, which provide the impact strength of the polymer. Creep test, dynamic mechanical, fatigue test, hardness. Okay, so how we characterize our polymer. So these are the tests. By that we can say that our polymer has this type of property and it can be used for this particular application. Okay, so these are the some tools or some experiment which are generally used for metals. Okay, so if you are comparing metals with polymer, Somehow you need to use these parameters. Okay, stress and strain we have already discussed. Force divided by area. Okay, stress F F upon A. Similarly, strain change in dimension divided by the original dimension. Okay, change in dimension you can say delta I delta delta change the dimension divided by its original dimension. Okay, so you can write delta A upon A. Okay, so area is original, then how much change is there. So you can write like that. Okay, so see, it is explaining when tensile strength. So how you will able to measure tensile? So you need to apply force, means you are making tension in this specimen. So initially its length was xo, then after applying this force its length was increased xo to dx. Okay, so now you can say that how much deformation is there. So dx is deformation in length. Okay, similarly if you are applying shear stress. Okay, so you are applying shear stress. Okay, so you are applying two force in opposite direction on opposite plane. Okay, so it is shear stress. So after shear stress, this this phase is shifted by delta x. Okay, and theta. So like that uh, you can find out the deformation by shear stress also. Okay, so mechanical property deformation, various type of deformation are represented here: tensile, shear. Okay, so there are two type of shear stress. In cuboid shape, you can see opposite force are applying in opposite direction. In the cylindrical, you are going to rotate it. Okay, so how much stress is developing? So you can measure compressive, then flexural load, then oscillatory. So you are making you are means moving this like that, means you are stretching uh, what say you are stretching and compressing like that, not pulling, pull and push like that. Okay, pull and push, or you are rotating like that. Okay, so these are the different types. Okay, so this is the universal testing machine where you put the specimen and you will apply, and you can apply stress sigma upon f, and according to that you will able to find out what is the ultimate stress, ultimate strain for this property. Okay, so generally we measured engineering stress. So engineering stress is generally load original. Okay, so we do not change the area. Okay, so we just keep the area of initially used. Okay, so it is called engineering. But in true stress we just change cross sectional area. Okay, according to time, because cross sectional area will be changed. Okay, age it will be elongated. Okay, as it will be elongated, the cross this area which is cross sectional area will be changed. Okay, so if you are putting the cross sectional area of given time, then it will give true strain. Okay, so these are the two property. Similarly, it for true strain also, uh, we for engineering strain we use original length, but for true strain we used length at the given time. Okay, this slide is also explained very well in questions, so I think it is not required now. Okay, so there are some properties of polymer which are stiffness. Okay, ability to carry stress without changing dimension. Okay, so the magnitude of elastic module is measured by this property. Then elasticity. Okay, stiffness means up to here you can say. Okay, the ability to carry stress without changing dimension, the magnitude of elastic modulus. Elastic, the ability to undergo reversible deformation. Okay, so up to here it will give you, up to yield point it will give you elastic modulus. the ability of undergo reversible deformation or carry stress without suffering permanent deformation. It is indicated by elastic limit or the yield point. Okay. Then strength. So strength means how much ultimate stress can be handled by this polymer. Okay. So strength, the ability of sustain a load, dead load. Okay. At the point, the polymer will be broken. Okay. So how much load it can be carry. So it is represented by tensile strength. The strength at specimen will be ruptures. Then the toughness. So up to here, how much energy it it sorry. Okay. So so this complete area up to here to okay. So this complete area will represent the energy of toughness. Okay. This area will represent toughness. Okay. The energy spent in causing a material to fail is in a tensile test. The area under the stress strain curve represent a measure of toughness. Okay. So these are the some property where elastic modulus of polymer, composite, graphite, ceramic, and metal alloy are represented. Similarly, stress strain curve are compared for polymer, metal, and ceramic. Okay, so ceramic are very you can say it can handle higher stress, but strain it cannot be deform means largely. Okay, so if you continuously increase the stress, it will be rupture, but it will not deform. Okay, metal can deform up to some extent, but polymer can be deformed largely. These are the some techniques which used to analyze impact test for the polymer. Okay, so these are very simple. I think you know about charp impact test. Okay, so the both ends are fixed. Then one notch is there, and you are making some load, so hitting by load, and you are rupturing it and measuring that how when it will be ruptured. Here in notched notched iso test. Okay, so one end is free and another end is captured, and again the same test is okay in tensile. So one the uh, dog bone sample, one end is fixed and another stress is given, and we are measuring that when it will break. Then folding dot test. Okay, so these are the very simple tests from where you can measure the impact. Okay, then Poisson ratio. So what is the Poisson ratio? Poisson ratio is nothing but uh, change in width divided by change in length. Okay, so width strain and axial strain. Okay, so if any specimen will be elongated, its length will be increased. Okay, but its width will be decreased, you can say. Okay, so that's why this ratio is also important. Okay, and it is vary for metal. So it is highest for metal, you can say. Sorry, it is highest for polymer. Means we can say that in polymer the width will be decreased more compared to length increase. Okay, that is only meaning, means Poisson ratio is higher, so width will be increased more. Okay, delta W upon delta. Okay, so these are I have explained many concepts. If you have any doubt up to here, you can ask, or it will be the end of this class. Okay, any doubt up to here? Any doubt, or you have any further doubt, or you have any doubt from your assignment? You can ask in 5 minutes. 5 minutes or more. I am here. Okay. After 5 minutes, I will close this class.